Okay, so as usual, any questions that you have, you can ask within the meeting. So you don't have to just put on your mic when you're ready if you have any questions, and feel free to interrupt if you have a question midway. You don't have to wait until the end of the solution to ask the question. So the first question is here, and it says the following. What is the unit digit of the following number? So definitely it's possible to do this quite fast with a calculator, but we want to use techniques that don't require a calculator. So if you don't have a calculator, what would be your strategy for this? Maybe I can give you 1 minute to see if you can figure out something. Then we can move to the solution. The number is 1 cubed minus 2 cubed. The signs are alternating, negative, then plus, negative, then plus, and so on. If you have any ideas, feel free to share. Okay, so maybe we can now proceed to the solution. So one way to do this is to look at the last digits of each of the numbers, because the unit digit will be made up, rather you can find the unit digit by finding the last digit of each of these numbers. So if we go to the solution, you will, let's first go back to the question. The last digit of 1 cubed will just be 1. The last digit of 2 cubed is just 8, or that the unit digit. The unit digit of 3 cubed is 7, and so on. The unit digit of 4 cubed is what? Is it 4? For 5 cubed, it's 5, and so on. So you keep doing this, and you'll find that the unit digits will repeat after some time. You will go all the way to 9, and then they'll repeat. These same unit digits will repeat. And you obtain the unit digit of that complete expression by applying the same signs to each of the unit digits that you obtain. So 1 minus 8 plus 7 minus 4, and so on, out to plus 9. And then you multiply by 2. And then the unit digit of 10 is 0. That's why you have 0 here. So 0 is out because it's a unit digit of 10. And the rest of them will appear twice, and they're still 0. So everything still gives you 0. So the unit digit turns out to be equal to 0. You can try this out yourself and convince yourself that these unit digits will repeat. That's why I've multiplied them by 2. So we move on to the second question today. So the second question says the digits of a 3-digit number ABC will satisfy this equation: 49A plus 7B plus C is equal to 286. So the challenge here is to find the 3-digit number ABC. Again, I can give you a minute to put together some ideas. If anyone comes up with a solution that fast, please feel free to share. Doesn't have to be a solution though. Even if you have some ideas on how to move forward, you can share them. So any ideas, if you have any ideas, just put on your mic and share. If you have started halfway and you feel you're headed in the right direction, you can share the ideas. Okay, so I think we can move to the solution, unless there's someone who still thinks they need more time. Okay. So I'll move to the solution. So these are both divisible by 7. That is one thing you will note, and we shall use that fact. 49 and 7 are both divisible by 7, and we shall use that. So that means if you add these two numbers, 49A plus 7B, you can write them as a multiple of 7. So the whole of this expression, 49A plus 7B, can be replaced by a multiple of 7. So if you go back here, we can replace this by 7K plus C is equal to 286. So that's what we have here. 7K plus C is equal to 286. Now C is supposed to be a 1-digit number. It's just a single digit. So the only option you have here will be C is equal to 6. Because 280 is a multiple of 7. And that's the only multiple that will give you a remainder of a single digit number. So C must be equal to 6. So let's see if we can figure out the rest. So if C is equal to 6, it means this part, 49A plus 7B, must be equal to 280. That is, you subtract 6 from both sides of this. Once you subtract the 6, you are left with only 49A plus 7B, and on the other right-hand side, you are left with 280. So if you divide both sides by 7, you will have 7A here, you will have B here, and you will have 40 on the other side. So again, this means we know that B must be a single-digit number. The only multiple of 7 that will work here is 35. That means B must be equal to 5. And if B is 5, A has no other option but to be equal to 5. We are sure that B must be equal to 5 because B must be just a a single digit number, a number between 0 and 9. And this definitely cannot be 0. The only other option that can work is 5, because the closest multiple of 7 will be 35. So that solves the problem. It means we have all the 3 values, A, B, and C, and the required number is there for 556. Is that making sense? Can you hear me? There's a lot of hello?
Yes, it is clear, sir.
Okay. Thank you. So now we have some question with a diagram. I hope you can see the diagram. Don't know if it's too small. So we have a figure. We have 2 squares in the figure, that is A, B, C, D, and D, E, F, G. And the bigger square has side length 5 centimeters, and the smaller one has 3 centimeters. So the bigger square is this one, A, B, C, D, and the smaller square is down here. So what we need to do is to find the area of the shaded region, ACF, that shaded triangle. That area is what we need to find. So again, I can give you a few minutes to figure this out. Maybe 1 minute. If you have any ideas, you can just put on your mic and share them. So maybe I can change this so that we are able to see the diagram better. I'll put it back into slide at some point. Let me change this magnification to 400. So this is what maybe this should be better now, the diagram, clearer. So the square, the big one, has side 5 centimeters, and this small square has side 3 centimeters. We just need to find the area of this shaded triangle, ACF. So, okay, I will move to the solution unless there's someone who wishes to give it one more try.
Oh, hello, Doctor.
Yes.
Oh, so I have an idea for the solution.
Yes.
Okay, so I'd say that you add another vertex on the top right side so that you have a complete rectangle.
Yes.
And then from there, you'll just subtract the. Okay, there you'll see that there'll be 3 right angles. So it's
Yes.
easier to compute the area of the right angles. So you'll subtract the area of the triangles from the larger rectangle.
Yeah, that's actually what we used in the solution. So we can just go through the solution. It's the same ideas that you have. So what he said is we construct an extra vertex here so that we complete this huge rectangle, right? So we'll define some notation first of all before we proceed. So this ABC is a triangle, and the area of that triangle is represented by the vertices written here, ABC, with the square brackets. So anytime you see the square brackets around a region, that means the area of that region, whether it's a rectangle or a triangle or so on. So this will mean the area of that region. So with that notation, we can check the following. So this ACF is what we are looking for. To obtain it, we need to take the area of the larger triangle, right? Then we need to subtract the area of ABC, which is easy to work out. We also need to subtract the area of AFG, and finally the area of CHF. So the dimensions of all these are known. If you work out those areas, you should end up with these as your numbers. So just double check that this is indeed correct. And therefore the area of the shaded region that you're looking for is 12.5 square centimeters. So these are, the trick was to complete this rectangle and then use that to find the areas. So we are on the last question now. Unless someone has a question on the previous one. Is this one okay?
Yeah, it is.
It's fine.
Yeah.
So we move on to one more. This will be the last question for the day. We usually do exactly 4. So here is this one might require a little more thinking. So let's see how it goes. So Juma picks a set of positive integers. All of them are less than or equal to 2004, such that none of the numbers in his set is twice the value of any other number in the set. So for example, if 3 is in the set, 6 cannot be in the set. The question is, what is the largest possible number of integers in the set constructed by Juma? So as usual, any ideas you have, you can share.
Professor, I have an idea.
Yes, John.
I have an idea of trying to include all the odd numbers in our set, and then try to fix in some other values of some other even numbers in between the odd numbers, which will not be twice any of the odd numbers given.
Yes, that's correct, but not complete. It's a
Okay,
first.
let me try to figure out how I can complete it.
Okay, we can give you 1 more minute.
Okay.
Or 2 more.
Okay, 2 more, or 2.5.
Okay, 2.5 it is. So if anyone has any new ideas, you can share as well.
Oh, sir, I think I've completed the solution somehow.
You want to describe it?
Yes, I want to describe it.
Yes.
So I will first of all list all the odd numbers from 1 through 2003. So intuitively, no odd number is twice any number. And therefore, we can maximize this set by trying to include all the odd numbers. And then after I include these odd numbers, so I can say these odd numbers are a subset of the whole set we are looking for. Then I will try to exclude all numbers equals to 2 times these odd numbers here. So for instance, if I can have another set which consists of 2n, where n is an odd number. So if I have 1, 3, 5, 7, 9, and so on, I can have another set with 2, 6, 10, and so on, simply twice this all these odd numbers. I realize it's an arithmetic progression with common difference 4 and first term 2. So if I can find the number of terms in this arithmetic progression, I will subtract it from the set of all even numbers and then get the number of other even numbers which I can include in my set. So precisely, there are around just a wee bit, I check the number of terms in my arithmetic progression.
Okay, you have some idea, but probably not the complete idea.
Oh, I see.
Yeah. Maybe we can look at the solution, but you have done a good job so far.
Sure.
Even a little more time, you would have completed.
Yeah, probably.
Okay, so I've understood what Yoshi has said.
Yes.
But so I think if you exclude the numbers that are twice odd numbers, you'll have there's a sequence. It will be 4, 8, 12, 16, and so on. But in that sequence, there'll be numbers which
you can't have 4 and 8.
Yes. Now I'm saying after you've excluded some of the numbers. So I think okay, I don't know how to explain it, but yeah.
But 4 must be one of the numbers so far. You can see why 4 must be one of the numbers selected.
Yes.
Okay, let's just go to the solution. But it's a bit tricky. It would take a bit of time to finalize it if you wanted to solve it. So maybe we can look at my strategy, what we worked with. So what we did here is to simply look for all integers which are divisible by 2 raised to 2k, but not divisible by the next power, that is 2 raised to 2k plus 1. So if you have an integer of that form, 2 raised to 2k, double that integer is kicked out, right? So as usual, you can take k is equal to 0. If k is equal to 0, then we just pick, that means you pick the odd numbers. So all numbers that are not divisible by 2, that is the odd numbers. So you'll have 1002 in total of those numbers. That's the first set that Yoshi picked. So that's the easy one to pick. So now you keep increasing the value of k. So when k is 1, this will be 4. You can't have 2 because once you pick, you can't have the numbers 2. You can't have 6 because you have the odd numbers in there already. So the next one you can pick is 4 because among the numbers you've already picked, none of them, 4 is not twice any of them. So the next one you pick is 4, which is 2 raised to 2, right? So that's when k is equal to 1. And then you'll find all those numbers that are divisible by 4, multiples of 4 that are not divisible by 8. This gives you, now in this set, you'll have 251 numbers. This function, this function here is the floor function. Let me just do something fast before we proceed. So if you have something like this, my drawing may not be properly done. So if I have that function and I have a number, say like 4.3, then what this means is that I take the largest integer that is smaller than this. So this floor function, the output is an integer, or rather, and that will be the largest integer that is smaller than the number inside there. These two, we call them, can I call them legs? Left leg and right leg. Yeah. So that's how it works. So for instance, if this was, it doesn't matter, as long as you have 4 here, even if it was 4.9, it will still be equal to 4. So I think that makes sense.
Yeah, nileweka.
Okay. So that's what this function means. So we do that for when k is 1. So the next number you can pick now is 16 because 8 was kicked out. The next one you can pick is 16 when k is equal to 2, and find all numbers that are divisible by 16, and kick out any number that is double any of the numbers in here. You end up with 63 of those. We continue with the same fashion. With k is 3, again, the next one we can pick is 64. We kicked out 32, so we can use 64. So 64, we look at all those numbers that are divisible by 64 and not divisible by 128. That gives us 16 of them. We continue in the same fashion. At the next point, we get 4 numbers when k is 4. And we keep going until we exhaust the cases. So when k is equal to 5, this is what we have. When k is 5, what we'll have here is 2 raised to 10. So all numbers are divisible by 1024, but not divisible by 2048. So this covers all the numbers that we are looking for. So we can just add up the numbers and we end up with our answer. The answer is 1,337. Is that making sense now?
Yes, it's making a lot of sense.
Yeah. Umeelewa.
Good. So this last bit just explains the notation. This flow function simply picks the smallest integer that is less than or even equal to a. I think that should be or. So the situation where you can have equality is if a is just a whole number 4 itself. So that brings us to the end of today's session. If you have any questions, please feel free to ask. If you have any comments, you can do the same. You can let us know.
Yeah, thanks Sana Daktari.
Yes.
The lesson was awesome.
Thank you. So we also putting in place some arrangements. The plans are still underway. They're not quite complete, but maybe sometime in November, we've been in discussions with some people from MIT, the Massachusetts Institute of Technology. I think I can stop the recording so that this one, we don't need it in the recording. So I'll stop the recording.